Hello and welcome back to Data Analysis and Visualization. I'm Jivita Christie, and in this video, I'm going to continue with hypothesis testing. And in the previous one, we saw p-value. This time, we're going to see the Pearson coefficient. So let's begin. Pearson's correlation coefficient. It is usually denoted by R, and it tells us about the strength of the linear relationship between X and Y points on a regression plot. So if you have studied statistics at all before, you already would know what regression is and specifically what linear regression is. Now, what exactly does that mean? What exactly is linear regression or a linear relationship between two variables? So let's take an example. So what you see here is an example. And in this example, there are different people. There are 10 people with their ages and their annual income. So we want to find out if there is a linear relationship between age and annual income. And what you see here written as subject, that is actually just a serial number given to each person. And there is age given and there's annual income given. So what we want to find out is if this person is having this much annual income, is there any connection between the age of that person and the income? So is there something like, if a person is older, then he or she might have higher income, or if the person is older, he or she might have less income. So is there any such connection? That is what we need to find out, and that is a linear relationship. So what we do is we basically plot all those things on a graph, and you can see there's x-axis and y-axis. X-axis contains age and y-axis contains the income. And you can see the blue dots present here. Those blue dots are the 10 points which we just saw in the table previously. Those points have been just plotted over here on this graph. And using that, we're going to see if there is any linear relationship between these things, between the age and the annual income. So when we do a hypothesis testing with Pearson or with Pearson's correlation coefficient, it tells us whether we can conclude that two variables correlate or influence each other in a way that is statistically significant. R measures the strength and direction of a linear relationship between two variables on a scatter plot. So because we have two variables here, when we talked about p-value, we were talking just about one variable. But now we want to measure something else. That time we were just trying to measure, about whether or not the medicine works. So that was a different type of a hypothesis. Here we are trying to test a hypothesis whether one variable affects another variable, whether one variable influences another variable, whether age can determine somebody's annual income, whether somebody being older might mean having more income or less income. So if this influence is statistically significant, then we can say that there is a linear relationship between them. So when we talk about R, which is Pearson's correlation coefficient, we are not just talking about whether or not there exists a linear relationship. We are also talking about the strength of that relationship, to what extent one variable affects another variable or influences another variable, and also the direction, which is important because we want to know whether being older means earning more or being older means earning less. So that there the direction matters, whether it is a positive correlation or a negative one. Whether if one variable increases, does the second one decrease or increase? So if that sort of a relationship is also into the picture when we talk about Pearson's correlation coefficient. And if we can find this R, if we can find the value of this R, then we can answer all these questions. So R typically ranges from -1 to +1, and values which are close to 0 would indicate no correlation. So if you have R which is 0.0000 something, then it shows that there is no correlation. If the value of R is -1, or somewhere closer to -1, then it indicates a strong correlation, but the correlation is inverse, which means when one variable increases, the other decreases. When that one decreases, the other one increases. So that is an inverse relationship if the value of R is negative. If the value of R is positive, which means from 0 to 1, and as close to 1 as possible, then it shows a strong correlation and it indicates a positive relationship, which means if one variable increases, the second one also is bound to increase. So that's what Pearson's correlation coefficient is. And in a short while, we are going to see how we can actually find that value. Here are some scatter plots showing you what exactly the coefficient looks like. What is the value of the coefficient when the scatter plot looks like this. So this is one of the scatter plots, and here you can see the value of R is 0.4, which means there is a correlation, and because R is positive, it is a positive correlation where if one variable increases, the other one also increases, or if one decreases, the other one also decreases. And this is no correlation because R is 0. You can see a flat line on the scatter plot, which means one variable does not influence the other one at all. And then you can see this third one, which is negative correlation, where the value of R is -0.4. In this case, if one variable increases, the other one is going to decrease, and if one decreases, the other one's going to increase. So this is what the scatter plot of that would look like. And now we come to the formula of R. This is the formula right here, and it might seem a little bit, foreign and huge, but it's very easy to understand. What we are talking about here, x and y, they are the two variables that we are talking about, and I is equal to the number of paired samples. So we just want to measure I is just equal to 10 in our case. So I will be 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10 in our case because there are 10 values. And sigma xy is the sum of products between the paired scores, which means age and income. So we will be just multiplying each age with income and take the sum of that. So that would be sigma xy. Then we have sigma x, which is sum of x scores. So consider age as x, then sigma x would be the total of all the ages. Then we have sigma x square. Sigma x square is sum of squared x scores. So if you're talking about x as age once again, then you take squares of all the ages, and after taking the square, you can add all the squares together. And the next one is y square. So if you're talking about y as income, then you would take squares of all the incomes and then do a total of that. And once you have all these values, and one more thing is what is n? So n is the total number of observations you have, in our case 10. So whatever that value is, now we just have to put that into this formula and we are good to go. We just have to, use the calculator and we can find the answer to that. So that's how you can calculate R using this formula. We are going to do that in a short while. So calculating R, the first step is to define null hypothesis. Because we are beginning to do a sort of an experiment or simulation, we want to make sure that we have a null hypothesis, something to fall back to if this does not work. So the null hypothesis would be that there is no correlation between income and age. And our alternative hypothesis would be that there is a correlation between income and age. Either there's a positive correlation or a negative one. We do not know yet, but we'll find out when we find R. So that is our null hypothesis, because we always need to either prove the null hypothesis or disprove the null hypothesis. The second step is to define alpha. It is our measure of significance strength. So a lower alpha is going to be a stronger alpha. So just like in the previous video when I talked about p-values, we defined a threshold value over there as well. To know that, if we calculate the p-value, then what is our threshold? Up to what extent we want the p-value to be? We want it to be less than this particular threshold. Only then we can either prove or disapprove our null hypothesis. So in a similar way, we are going to define alpha here, which is taken as 0.05, which is usually the value taken for alpha. The third step is to find degrees of freedom. Now our sample has 10 subjects. So the formula for finding degrees of freedom, which is denoted as df, is equal to n minus 2, which is 8 in our case. So we found the alpha, we found the degrees of freedom, df, which is 8. Now the fourth step is to use an R table, and in a short while I'm going to show you the R table itself. But what you have to do there is find a critical value or a threshold value that you can use to either accept or reject the null hypothesis. So in our case, we are going to use the value of alpha that we defined, which is 0.05. We are going to use the critical, we are also going to use the degree of freedom, which was 8. And now using that, we are going to find the critical R, which will come out to be 0.632. I'm going to show you that in a short while. Now, if our R, which means our Pearson's correlation coefficient, is greater than the critical R, then we reject the null hypothesis. But if it is lesser, then we approve the null hypothesis. So that's what we do. And obviously, when we reject the null hypothesis, then it means that we are actually agreeing, or rather proving, the alternative hypothesis. And the last step is to apply the formula of R, which I showed you earlier. So make all those calculations, put the values in the formula of R, and find the actual value of R. So let's try it out with our age and income example. And before that, let me show you the table. So this here is the critical R table, which I have taken from this website. You can see down below. You can also use it really. You don't need to memorize all these values. In this table, you can see degrees of freedom mentioned. That's the first column. And what you see on top is other columns, which you see they are values of alpha. So in our case, the degree of freedom is 8, and the value of alpha is 0.05. So it falls somewhere here. It intersects right here. So that's why we get 0.632, which we are going to use as our critical R value. Now let's calculate. So for calculation purposes, you can see this table I have calculated already, and these are the answers. If you wish to calculate on your own, you could pause the video here, try to do your own calculations, and then come back and verify your answers. So I'm going to just very quickly tell you what this calculation is about. So you can see subject column, that's nothing new. X and Y columns, X is the age, Y is the income, annual income. Then I've calculated X square. So X square is simply square of X. So 22 into 22 gives you 484. 55 into 55, 3025. So that's how X square is calculated. We've also calculated Y square. Y square is the square of all the values present in the Y column. So 35,000 square is this big number right here. And so we have squared each and every Y value present. Okay, and then we have taken a multiplication between x and y. You can see multiplication between x and y. So we're just multiplying 22 with 35,000 and we are getting here 7,70,000 as the first value. So that is how it is calculated. We have all these columns. In the bottom of it, you can see everything is summed up. So I have done a summation, a sigma function applied on all the columns. So even those values are available. And now you just need to recall the formula that we had and simply use this formula and put all the values. We have already calculated everything necessary for this formula to work. So we just need to place all those values now. And so we are first, the topmost thing would be 1305000, as you can see. And in the bottom part, we have 39.67, multiply that by 68223.16. And finally, you will get the value of R as 0.482. You can check this out for yourself. Try to calculate and see what the value of R is. So this is the value of R. Now, what does that tell us? What does this value of R show us? So first, does it exceed our critical R? Do you remember what the critical R was? The critical R was 0.638, I think. So it does not exceed, right? 0.632. Our value of R that we have calculated is 0.482, and our critical R was 0.632. And obviously, our Pearson's correlation coefficient is less than the critical R, and therefore we accept the null hypothesis and we say that there is no correlation between age and income, which means age and income are not influencing each other. A person being older doesn't mean it doesn't mean he has more income or less income. So this is our conclusion based on the calculation of R and the data that we had. So I hope you understood all this, and I'm going to continue with creating videos for data analysis and visualization. So I'll see you in the next one, and thank you for watching.